All right, our last topic for chapter 3. Again, it might cross over into chapter 4. I don't even know where this one is anymore. But the last type of reaction, probably the hardest one for most people, are oxidation reduction reactions. We often combine that and just call them redox reactions. But essentially what that is a reaction in which, by definition, it's a reaction where one element in one compound will give up electrons and give the electrons to another element, usually in a different compound. When the electrons get changed from one element to another, the element that gives the electrons away, its charge is going to go up. The element that we give the electrons to, since electrons are negative, its charge is going to go down. So we recognize a redox reaction by the fact that two of the elements are going to change their charges. When one charge goes up, the other charge goes down. That's the oxidation and the reduction that are occurring. Okay? So, if I look at a reaction, how would I know whether the charges are changing? And by the way, we're going to cheat a little bit in this section. When we deal with ionic compounds have charges. So like sodium chloride, the sodium is +1 and the chlorine is -1. When we deal with covalent compounds, like water, we usually say the hydrogen and oxygen in the water molecule, since it's covalent, they're sharing electrons instead of exchanging electrons. So they don't technically have charges. But then when we get in this section, we treat them like they do. Instead of calling them charges, we're going to call them oxidation numbers. Okay? So in the water molecule, even though the hydrogen and oxygen don't have charges, we're going to assign them oxidation numbers, and it's just like charges. In the water molecule, hydrogen would be +1, the oxygen would be -2, but since there's two hydrogens in a water molecule, the 2 + 1s cancel out the -2, so it still ends up being neutral. Okay? Again, it's kind of a cheat, but it's an important concept in chemistry that allows us to do a lot of other things. So, when I look at this reaction is a redox reaction. The elements in this reaction are changing their charges or changing their oxidation numbers. Okay? Now, how do I know that? Well, again, this is a place where people get stuck a little bit. If I ask the class, this is usually where I kind of make fun of people a little bit in a normal class when I actually have people in the room. I hate being by myself. But if I ask the class, what's the charge of sodium? Everybody looks at the periodic table, sodium's in group 1, and they'll say +1. That's wrong. The charge of sodium right now, this is just elemental sodium. If it had a charge, I would have to put the charge right up here above it. Okay? And it doesn't have one. When an element is in its pure form and it doesn't have a charge shown, its charge is 0. Now, when sodium forms compounds, it likes to get rid of an electron as it forms the compound and become +1, but that's only when it's in a compound. When it's by itself, it's stuck with its electrons, even though it doesn't want to have 11 electrons and 11 protons, it's stuck with all those electrons until it has a chance to give them away. Okay? So, elemental sodium has no charge. What's the charge of oxygen? This is where I really get people, because sometimes people still shout out -2, and that's wrong. This is oxygen gas. Pure oxygen has no charge. Okay? But neither one of these elements really wants to be neutral, because by gaining and losing electrons, they get to be like noble gases. That makes them more stable. So oxygen wants to gain 2 electrons. Sodium wants to lose an electron. They want to take charges so they can be like noble gases. That's how they want to be, but they're not like that yet. Oxidation number is 0, oxidation number is 0. Okay? But when you put them together, sodium has an opportunity to say, oh, now I can finally get rid of that one electron I didn't want. I can give it away. And oxygen can say, oh, okay, I'll take it. Actually, I need 2 of them. So basically, 2 sodium atoms are both going to give their electrons to 1 oxygen atom, so that oxygen, by getting 2 electrons, becomes -2, but each sodium only wants to give up 1. So that's why it has to be 2 sodiums for every oxygen to give me the charges that I want. Okay, once we form the charges, that's when these ions are going to stick to each other. The negative ion and the positive ion stick to each other, and they're going to form an ionic compound. All right, now in that process, sodium was neutral, and then it gave an electron away. So now over here in this compound, sodium has a +1 charge. So sodium went from a 0 charge to a +1 charge. That's the definition of oxidation. Okay, there are a couple of mnemonic devices. You can remember the term oil rig. Oxidation is losing. Reduction is gaining. Oil rig. So we're talking about electrons. Oxidation is losing electrons. Reduction is gaining electrons. So sodium was neutral. It gave an electron away to, so sodium gave an electron away to the oxygen. So sodium lost an electron. Oxidation is losing. Okay? Now there's another way of looking at it that I use myself. I look at the charge. Sodium's charge goes from 0 to +1. As you go from left to right, if the charge goes up, that's oxidation. If the charge goes down, that's reduction. I'm reducing the charge. So you can remember the oil rig thing, or you can look at the charge like I do. Either way is fine. Okay, it just depends on how you want to learn. So sodium's charge goes from 0 to +1. Sodium is being oxidized in this reaction. Oxygen is going from 0 to -2. If it goes from 0 to a negative number, that's going down. So oxygen is being reduced. Okay, so that, and by learning it this way, the oxidation reduction process, we're kind of trying to understand more about how this reaction actually occurs. So this is like a deeper look into how does the reaction happen, how are the atoms changing during this process. Okay, so a redox reaction is any reaction where the elements are exchanging electrons between them like that, which causes a change in the charge. So if I look at this one, if I want to know what's being oxidized and what's being reduced, then I have to be able to assign the charges to everything in the reaction and then look for which things are changing. So let's do it. In HCl, I'm not even worried about the 2 in the front. That's part of balancing equation. I'm just looking at the compound. The compound is HCl. The oxidation numbers, hydrogens can be +1, chlorines -1. I know that based on where they are on the periodic table. Iron, this is just pure elemental iron. Its charge is 0 because it hasn't combined with anything else yet. It's just a piece of iron. It has all of its electrons. Come over here. So I got +1, -1, and 0. You kind of have to make a note of all those charges. Then I look over here. Now I know hydrogen is by itself, so it's going to be 0. Anytime you have one by itself, that's the easiest one to look at. So hydrogen 0. Over here, I know that chlorine always likes to be -1, and there are 2 of them. So that's going to help me get iron. Now, why do I need help with iron? Well, if you look at a periodic table, iron's a transition metal. It's right out in the middle of the table. It's one of the ones that we don't know what its charge is going to be. Sometimes, and you don't need to memorize them, but like iron can be either +2 or +3. But there's no way to know which one it's going to be unless you look at the compound. Since it's only combining with 2 chlorines, and I know that chlorine's -1, that means that the iron has to be a +2 because the charges in this compound have to add up to 0 if it's a neutral compound. Which, if it doesn't have a charge up here, then I know it's neutral. Okay, so based on all that, I can look at this and say, okay, hydrogen was +1 and it went to 0. +1 to 0, the charge went down, that's reduction. So hydrogen was reduced. The iron went from 0 to +2. If the charge goes up, that's oxidation. And then chlorine was -1 right here. it's still -1 over here. So chlorine didn't change. It was not oxidized or reduced. It was a spectator. Okay? It's just a spectator. And this, what kind of reaction is this? It's a single displacement reaction. Iron jumps in and is trying to kick hydrogen out. Okay? When it does that, the chlorine just stands there and lets iron and hydrogen kind of duke it out to see who the winner is, and chlorine just goes with the winner. Okay, so again, if we're getting back to our sexist example, that's really bad. Anyway, so that's our redox approach. Okay, we're looking at how the charges of the atoms are changing, and why does it happen? It's because of the exchange of electrons that's occurring. All right, so next slide. Now, really the hardest part about this section is that initially when you guys start looking at a whole reaction with a lot of compounds in it, you have to be able to go through and assign the charges to all the atoms. And that takes practice and that takes time. Okay, so how do we assign the oxidation numbers or the charges? Well, basically here's a few rules. First of all, if I have a monoatomic ion, so just like chlorine with a -1 charge, the oxidation number is the charge. So if I have Cl minus, that means the oxidation number is -1. If I have a pure element, like oxygen gas, or a piece of iron, or a piece of sodium, the oxidation number will be 0. Any pure element in its normal form, the charge is going to be 0. And then when I form compounds, I have some general guidelines that I usually follow. Okay. Now some of this is going to, chemistry's hard because whenever we learn a topic, sometimes it's related to other topics that we haven't covered yet, and it's hard to fully explain things without touching on things that haven't come up yet. So here, in order to do the oxidation numbers, you have to be familiar with a property called electronegativity. Electronegativity comes up in chapter 7 and chapter 8 when we learn more about the periodic table. But the general idea, if you're looking at the periodic table, the element that is the most electronegative, if we go all the way up to the right in the upper corner, and we're going to ignore the noble gases because they don't form compounds. But in the upper right corner, fluorine is the most electronegative element. Okay? Which means it wants to have a negative charge more than any other element on the periodic table. It's the strongest. So anytime fluorine forms a compound, it will always get its normal negative charge, which is -1. Okay? Now, right beside fluorine is oxygen. He's the second biggest bully. He will always get his normal negative charge. When you combine oxygen with any other element, he's always going to get to be negative unless you put him with fluorine. Fluorine's stronger. So if you put oxygen with fluorine will be -1, and the oxygen's going to have to be positive because the fluorine's going to take electrons from him. But oxygen's strong enough, if you put him with anybody else, then he's going to take their electrons. Okay? So oxygen's always going to be -2 unless you put them with fluorine, or there is a weird group of compounds called peroxides. If you happen to have a peroxide, then oxygen's -1. But again, that's like a special case. You don't see it a lot, so don't overly worry about it. But essentially, fluorine's always -1. Oxygen's pretty much always -2. And then hydrogen's usually +1. And then anytime you're looking at different elements, like if you have two nonmetals, and you're like, okay, which one's negative, which one's positive? The one that's further up in the upper right corner, closer to fluorine, that's going to be the one that's more electronegative. That's the one that gets the negative charge, and the one that's further away is going to have to take a positive charge. Even if it doesn't want to, he'll have to. Okay? And then finally, when we're looking at a compound, usually if you can figure out some of the oxidation numbers, then if you know that the sum of all the oxidation numbers in a compound, if it's a neutral compound, the sum of all the charges has to add up to 0. If it's a polyatomic ion, all the charges have to add up to the overall charge. Like for phosphate, PO4, the charge is -3. So I know the oxidation numbers of the phosphorus and the 4 oxygen atoms, they have to all add up to equal -3 to make phosphate. Okay? So the sum of all the oxidation numbers has to equal the overall charge of whatever it is you're looking at. So we can practice a little bit real quick. I got about a minute on my video. So in HCl, the oxidation numbers, if you just look at it, and again, stop the video, look through these compounds, assign them, and then I'm going to talk through it real quickly. So in HCl, the sodium's going to be +1, chlorine's -1. That one's easy because they match up with their normal charges. N2O, if I look at these, they're both nonmetals. They both want to be negative. They can't both be negative. So the one that's closer to fluorine is oxygen. So oxygen gets to be -2. Nitrogen's going to have to take a positive charge. And I know it's neutral because this compound has no charge up here. So if oxygen's -2, nitrogen has to be a +1 because with 2 +1s, there's 2 nitrogens here. +1 +1 -2, that gives me my 0. The charges have to add up to 0. Okay? Then in NO, again, oxygen's -2, but this time the nitrogen has to be a +2 because they have to add up to 0. NO2, again, oxygen's -2. Each oxygen is -2, that's what the oxidation number is. But together they make -4, so that means nitrogen has to be a +4. CO, oxygen's -2, carbon's +2. CO2, oxygen's -2, but there's 2 of them, so that means carbon has to be a +4. Nitrate, don't forget the -1 charge. Each oxygen's -2. There's 3 of them, so that makes -6. But in order to get the overall charge of -1, if I have a -6 here, that means nitrogen has to be +5. So I got +5, and then each oxygen is -2. Those are the oxidation numbers. I got to cut off before the video.